Welcome network engineers. Today we will master the NVIDIA Spectrum-X networking platform. We will move beyond basic connectivity to cover advanced configuration via NVUE, optimization for AI workloads using Rossi and adaptive routing, essential security hardening, and deep troubleshooting with WJH and NetQ. Let's get started. To begin, we must understand that Spectrum-X is not just a switch, it is an end-to-end platform designed to solve the bottlenecks of traditional Ethernet in AI workloads. Traditional Ethernet often struggles with the synchronized bursty traffic of AI training. Spectrum-X addresses this by tightly coupling the Spectrum 4 switch with BlueField-3 Super NICs. This combination allows us to achieve performance isolation, ensuring that one tenant's heavy workload doesn't degrade the performance of another. This architecture is critical for running massive transformer-based models efficiently. So what have we learned? We've established that Spectrum-X is a purpose-built platform that integrates switch and endpoint intelligence to solve specific AI congestion and latency challenges. Let's visualize the Spectrum-X flow. Starting on the left, your AI workload generates massive data bursts. This traffic hits the BlueField-3 Super NIC. Unlike a standard NIC, the Super NIC coordinates with the Spectrum 4 switch. The switch doesn't just forward packets, it uses advanced telemetry to perform adaptive routing across the fabric. This ensures traffic is load balanced dynamically before reaching the destination, maximizing throughput. Now let's look at how we configure these devices. We use the NVIDIA User Experience or NVUE. NVUE represents the entire system state as a structured object tree, removing the ambiguity of context-specific commands. A critical concept here is the pending versus applied state. When you issue a set command, you are only staging the change. You must explicitly run nvconfig apply to push that configuration to the running system and nvconfig save to persist it to startup. This prevents partial configurations from breaking the network. What is the key takeaway? NVUE provides a safe API-first approach to configuration that prevents accidental outages by requiring explicit application of stage changes. This state diagram illustrates the NVUE workflow. You start by issuing nvset commands, which moves the system into a pending state. Nothing changes operationally yet. You then execute nvconfig apply to make those changes live in the applied state. To ensure these changes survive a reboot, you must transition to startup using nvconfig save. Note that you can also discard pending changes if you make a mistake. Optimization in an AI fabric revolves around Rossi. We must minimize latency and packet drops to keep GPUs fed. Spectrum switches allow us to configure RDMA over converged Ethernet easily, while you can manually tune priority flow control, PFC, and explicit congestion notification, ECN. NVUE provides a powerful shortcut, nvset QoS ROS. This single command applies NVIDIAS validated best practices for buffers and traffic classification. We generally recommend lossless mode for AI, which uses both PFC to pause traffic and ECN to signal congestion. Why is this important? Because correct Rossi configuration prevents head-of-line blocking and ensures the high throughput required for training runs. Here we see the Rossi congestion control loop. The sender transmits data at a high rate. The switch detects that its buffers are filling beyond a specific threshold. Instead of dropping the packet, the switch marks it with ECN, explicit congestion notification, or uses PFC frames. The sender receives this signal and reduces its transmission rate, preventing packet loss. The switch then forwards the packet to the receiver smoothly. For hyperscale AI, standard ECMP, equal cost multipath hashing, isn't enough. It can lead to collisions on specific links. This is where adaptive routing comes in. Spectrum 4 switches evaluate congestion on every egress queue and reroute traffic on a per-packet basis to the least congested port. This is far superior to flow-based hashing. While this causes packets to arrive out of order, the BlueField-3 Super NIC handles the reordering transparently. To enable this, we use the nvset router adaptive routing command. What have we learned? Adaptive routing is the key to achieving up to 95% effective bandwidth in AI fabrics by eliminating static hash collisions. This diagram explains adaptive routing logic. A packet enters the switch. The logic immediately checks the congestion levels of available uplink ports. If port 1 is busy, it routes to port 2. If port 2 is busy, it tries port 3. All packets travel through the fabric and arrive at the BlueField DPU. Crucially, the DPU reorders these packets before delivering them to the application, ensuring data integrity despite the scattered pathing. Performance means nothing without security. We must secure the management, control, and data planes. First, apply control plane ACLS to restrict who can talk to the NVUE API or BGP ports. Second, ensure all sensitive configuration data such as radius secrets or BGP passwords utilizes NVUE's built-in database encryption. For data in motion, particularly across data center interconnects, Spectrum supports MACsec to encrypt traffic at layer 2. Why is this vital? An unsecured high-performance network is a high-speed vector for attacks. We must lock down the control plane to maintain fabric integrity. This diagram maps our security layers. The overarching security layers class includes control plane ACLS, encrypted storage, port security, and MACsec. These mechanisms inherit down to protect specific domains. Management VRF is protected by ACLS, the data plane is secured via MACsec and port security, and the configuration database uses encryption for secrets. When packet loss occurs, we don't guess. we use what just happened, WJH. WJH is not just a counter. It captures the context of the drop directly from the ASIC. It tells us exactly why a packet was dropped, whether it was an ACL denial, a buffer overflow, or a routing loop. You can view this directly on the switch using NV Show System WJH Packet Buffer to see a table of drop reasons and affected flows. What is the key takeaway? WJH moves US from "I think we have packet loss" to "we are dropping packets on port 5 due to an ACL mismatch," drastically reducing mean time to innocence. This flow shows the WJH lifecycle. A packet ingresses and hits the forwarding engine. If an error is detected, it triggers a drop event. The WJH agent immediately captures the packet header and the specific reason code from the ASIC. It then simultaneously streams this telemetry to the NetQ UI for historical analysis and stores it locally for immediate CLI troubleshooting. For broader fabric issues, we use NVIDIA NetQ. NetQ aggregates data from agents running on every switch and host. Its most powerful feature for Spectrum X is flow analysis. This allows you to trace a specific application flow across the fabric to see exactly which path it took and where it encountered latency or buffer contention. It also functions as a time machine, allowing you to look at the network state during a past event. Why use NetQ? Because it correlates configuration state with operational state across the entire fabric, identifying misconfigurations that single switch CLI commands might miss. The NetQ architecture is centralized. The NetQ agent resides on your switches and hosts, pushing telemetry to the NetQ server. The server stores this in a specialized telemetry database. You, the user, interact with this data either through the command line interface for quick queries or the GUI for visual flow analysis and heat maps, both querying the central server. To conclude, managing SpectrumX effectively requires a lifecycle approach. Start by validating your designs in NVIDIA Air using a digital twin. Use Ansible and NVUE to automate your deployment to ensure consistency. Once deployed, rely on WJH for granular drop detection and NetQ for fabric-wide visibility. Remember, AI workloads are unforgiving of latency and packet loss. By applying the optimization and security techniques we discussed today, you ensure your network powers the AI revolution rather than hindering it. Thank you for watching. This final diagram represents the continuous life cycle of a healthy SpectrumX fabric. You design and simulate in NVIDIA Air. You deploy and configure using NVUE and Ansible. You optimize using ROCE and adaptive routing features. Finally, you monitor and troubleshoot using NetQ and WJH, feeding those insights back into your design for the next cycle.